All right. Good morning, everybody. Thank you for being here today. We want to thank you for coming, thank the speakers for accepting our invitations. We are very excited to be here at the 2019 Operations Research Center IAP seminar on machine learning and operations research. So very quick outline of the schedule today. It's going to be 2 talks, then a panel discussion with practitioners from the industry, and then another 2 talks. So I'm very delighted to introduce you to our first speaker, Professor Negin Golrezaei. So Professor Negin Golrezaei is an assistant professor in operations management at the MIT Sloan School of Management. Her research interests lie in machine learning, statistical learning theory, mechanism design, and algorithm for optimization when applied to pricing, revenue management, and online markets. Before coming to MIT, Negin was a postdoc fellow at Google Research in New York, where she developed and tested algorithm for online marketplaces. She has been awarded multiple awards in the last years, for example, the Danzig Dissertation Award in 2017. She earned her Bachelor of Science and Master of Science in Electrical Engineering from the, from the Sharif University of Technology, and her PhD on operations research from USC. So thank you, Negin, for accepting our invitation. I'll let you present us your talk. Thank you very much.
So first of all, thank you very much, Nicholas, for such a comprehensive introduction. And thank you, everyone, for coming to this talk. And again, I would like to thank again Nicholas and other organizers for inviting me. So today, I'm going to talk about robust pricing in contextual auction. And this is a joint work with Adel Javomard and Vahab Mirokni. Adel is at USC and Vahab is at Google. And this is a working paper. Because of that, your comments and feedback are more than welcome. If you have any questions, any feedback at any given time, just please feel free to stop me. So the main motivation behind this work is coming from display advertising market. So in display advertising market, our goal is to sell ad views to advertisers. And there are platforms such as Google AdX that runs auction on behalf of web publishers. And they actually run an auction in real time every time a user visits their website. And then when they run an auction, they send requests to advertiser, ask them to participate. Advertisers submit their bid. One of them is going to win the auction, and the ad of the winner is going to get displayed to the user. You will see something like that as a user. So one of the important things in display advertising market is setting right prices for advertisers. So when you want to run an auction, if you want to make sure that you get high revenue from advertiser, you really want to make sure that you set right prices for them. And in fact, there are a couple of papers that empirically show that if you do not set right prices for advertisers, you are going to leave a lot of money on the table. So our goal in this project is to find right prices for advertisers in display advertising market. So if you want to do that, there are 2 things that we really want to understand about this market. So first of all, this market is very contextual. So both sides of the market, platform as well as advertiser, have access to detailed information about the user who is visiting the website. How do they access to this information? They access it via HTTP cookies. And beside that, they know about the IP address of the user. They also know about the device ID that the user is actually using at that moment. So it's very contextual. And also, it's a very heterogeneous market. And here is why. Because advertisers get access to this contextual information, and they are going to react to that in a different way. And they are going to use this information to target internet users across different websites. And then when they target internet users, they are going to use their heterogeneous preferences. So as a result, we are going to end up with a very heterogeneous market. And in fact, in one of my recent work, we also show via analyzing Google auction data that, in fact, this market is very highly heterogeneous. So if the market is very contextual and it's very heterogeneous, if we want to set right prices for advertisers, we want to make sure that we set personalized and contextual prices. So by personalized, I mean that for every advertiser, we need to have a different price. And these price also need to change as we get a new context, as the user is changing. So you may say, this is not a big deal. Think about like Google AdX. So it's a really big company. They have access to tons of data. Maybe they can just simply use the historical data to optimize personalized and contextual-based prices. So yes?
Can we discuss what historical data? What does it mean, historical data?
Very, very good question. So by historical data, I mean that for every auction which is being run, you will see that what bid each advertiser submitted. And this is going to be the historical data. And on top of that, you will also get to observe the contextual information, meaning that for this cookie and for this website and for this time of the day and for this particular location, these are the bids submitted by the advertisers.
For every user that you have cookies
Think about for every auction, I have the submitted bids. And for every auction, I also have the contextual information. So, but then this typical approach seems to work, but there are challenges. So when you think about display advertising market, we are running billions of auctions just in a single day. And because of that, there are repeated interactions between advertiser and the platform. And also because, in fact, advertiser can be really strategic. There are empirical evidence that shows that they are, in fact, strategic. And then because of this repeated interaction, advertiser may have the incentive to manipulate your pricing policy. So to make it concrete, forget about contextual information for now and assume that I'm just using the submitted bids to set the price of a particular advertiser. So then in that case, the advertiser may have the incentive to lower his bid right now in order to pretend to have low valuation for this ad view in order to get lower prices in the future. And that's something that we don't want it to happen. So based on this, our goal is to design a dynamic pricing policy that obtains high regret, or in other words, it gets low regret. And then this dynamic pricing policy should offer personalized and contextual prices, and it should be robust to the strategic behavior of advertiser. So that's our main goal here. So in the rest of the talk, I'm going to go over the model, and then I'm going to show you two pricing policies. So the first pricing policy that we call it CORP, which is short for Contextual Robust Pricing. This gets the regret bound of log t squared. The second one that we call it SCORP, which is short for Stable Contextual Robust Pricing. That's actually for a slightly different setting and gets the regret bound of t to the power of 2/10. So I'll do my best to cover both of these policy, but it might be the case that in the interest of time, I may not go over the second policy. Okay. So, but then at the end, I'm going to finish with the main takeaway messages of today's talk. Okay. So here's a model. There are n buyers. So buyers are advertiser, and there is one seller. So the seller is Google AdX or any platform who is running an auction on behalf of a web publisher. And we have items that are arrive over time. So items are these ad views or ad impressions. And at any given time, we are selling one item. In each item is characterized by a feature vector x of t, where this x of t is a multidimensional vector, belongs to Rd. And feature vector is IID and is drawn from some unknown distribution. So distribution is unknown, but one thing which is important is that at the time of purchase, when we are selling that item, both seller and the buyer get to observe the contextual information. So let me illustrate this model via this simple figure. So at time t1, we get ad view 1. Then this is the context information of this ad view or the item 1. Then at time 2, we get another item with another feature vector, and etc. And as you can see, there is repeated interactions between the buyer and the sell side. And how we are going to sell the item? We are going to sell the item via repeated second price auction with reserve prices. And I'm going to show you, I'm going to get into more details how this second price auction is going to work. And then what about the buyer? So each buyer I has a private valuation VIT for the item being sold at time T. Again, that's something that I'm going to, I have another slide for that to show you the details how the buyer's valuation depends on the contextual information. Yes?
There are no budget constraints for the buyer?
No, there is no budget constraint. So in that setting, we assume that there is no budget constraint. But I think,
Realistic or not?
very good question. So so the main goal of this work is show that how we are going to make the mechanism robust. And in fact, we show that if you add the budget to this setting, using the techniques that I'm going to talk about, you still can get a robust algorithm. Very good question. So, okay, now let me talk about the second price auction with reserve prices and tell you how it works. Assume that we get one ad view at a time. Then, and here's the seller, and then we have here 4 buyers. So after observing this ad view, the seller is going to set reserve prices for different buyers. So we have 4 buyers here, and we have a buyer R1 for buyer 1, etc. So these are personalized prices. And these prices also depends on the contextual information for the ad view. Then the seller is going to share the contextual information with the buyer, and then buyer observe this contextual information. For example, the buyer learns that this user is coming from California, so something like that. Then the buyers are going to submit their bids based on the contextual information, and one of these buyers is going to win. In fact, the winner is the buyer that has submitted the highest bid, as long as the highest bid is above the reserve price of the winner. What about the payment? The payment of the winner is a maximum of the second highest submitted bid and reserve price of the winner. Okay. So why second price auction? Because second price auction, first of all, is widely being used in practice, and in particular widely being used in display advertising market. And it's a very simple auction format. It has a single parameter per buyer. It can be easily optimized. And if you look at this second price auction in isolation, just one single shot of second price auction, this second price auction is truthful, meaning that the bid of the buyer is going to be equal to their valuation. But then when we are running second price auction repeatedly and we have repeated interaction, things become more complicated. So in that case, both sides of the markets try to optimize their strategy. The seller would like to understand what are the optimal prices, and the buyers would like to see that how they can optimize their bidding strategy. And then if this happens, buyers may want to sacrifice their short-term utility in order to gain something in the future. So for example, they may want to lower their bid so that in the future they get lower reserve prices. Okay. And that's actually one of the main challenges that we encounter in this work. Sure.
The R1, R2, R3, R4. Are these the seller decides, but is this input for this problem, or is it part of the optimization of the seller?
You mean the setup buyers?
The reserves. Are the reserves input or subject to optimization?
No, this is a subject to optimization. That's actually our goal. So our goal is to optimize these reserve prices over time as we are getting these submitted bids of the buyers. So this, from the seller's perspective.
And there are no issues. The fact that the reserves are dependent on the buyer doesn't violate, I don't know this area well, but doesn't violate any truth-telling,
No, it does not. So even if you think about the Meyerson auction, which is the optimal mechanism, Meyerson goes beyond like personalizing reserve prices. They say that transform the bid based on the distribution of the submitted bid, and if the distribution of the bids is different, you are going to have different transformation for different buyers. Not only for even Meyerson auction, not only reserve prices are going to be different, also that how you are going to transform the bids to virtual bid is also going to be different. And then after you do this transformation, you do the allocation based on the transformation. So it's going to remain truthful. Yes.
So I understand, right? The reserve prices are different because the valuation is not IID. Different distributions.
Yes.
But are there any restrictions, not from the game theory point of view, and feel free to defer this question to later, but from a legal or ethical point of view, of having different prices?
So I don't know about that, but I think in current practice, personalized reserve prices are being used. So, and because it's being used, I think it should be legal. so that would be my answer. Okay. So what about buyer's valuation? So we focus on a linear model. So the valuation of the buyer I at time t is actually depends on the contextual information, is the inner product of the contextual information xt and this beta I, which we call it preference vector. And then we have this noise term, ZIT, which we call it market shock. So x of t, we already talked about it. It's the contextual information is known to the buyer and the seller. But the preference vector is not known to the seller, and that's something that the seller would like to understand. So for example, the seller does not know if this particular advertiser cares about the user from California or not. So that's something that the seller would like to learn over time. And then this market shock, the noise are drawn IID from some distribution F, where the distribution F is a log concave. And we consider two different settings. So in the first setting, the distribution F is known. And for that, we propose a policy that we call it CORP, Contextual Robust Pricing. And then in the other setting, we assume that distribution F is unknown. And we propose another policy that we call it a SCORP, a Stable Contextual Robust Pricing. OK, so now we know that what buyer valuation is. Let's understand what buyers actually care about and what they want to maximize. So buyers are utility maximizer, where the utility of a buyer at time t is the valuation of the buyer minus the payment at that time. So the utility is VIT, which is the valuation of the buyer at time t, times this QIT. QIT is this simple binary signal. It's 1 if the buyer I gets the item, and it's 0 otherwise. Okay. And then buyers cares about maximizing their cumulative time discounted utility, which is this UI. So you don't see it. OK, so this is this summation. And then one thing which is important here is this gamma here, which is a discount factor that we have here. So why do we have this discount factor? We have it here to model a situation where the buyers are less patient than the seller. And this is usually the case when this is usually the case for display advertising market, when advertisers really want to target a particular user sooner rather than later. So imagine that a user visits a particular website and click on something. This advertiser would like to show the ad of that particular product to the user sooner rather than later. And because of that, they are less patient than the seller. OK. What is our goal here? Going back to the Dimitri's question. So our goal is to help the seller to optimize reserve prices over time without knowing the preference vector of the buyers. And what's the main challenge? The main challenge is that the second price auctions are no longer truthful when we have repeated interaction. And then because these buyers are strategic and they care about their cumulative utility, they may want to manipulate the seller's pricing strategy in order to observe lower prices in the future. Any question about the model? Yes?
So the repeated XTs, both the sellers and the buyers know?
Exactly. This
historically.
Historically. And it's drawn from some IID, it's drawn IID from some unknown distribution. Yeah, it's a model.
In reality, there's no IIDs, you have XT.
Yeah, in reality, it's actually our result does not depend on the XT being IID. And even if the distribution can be anything, it still is going to work. But one thing is important is that both sides of our market can observe the X of T. Yeah.
Are they constant or time varying?
This is constant. So for example, if an advertiser would like prefer female user to a male user, that's going to remain the same across the time.
Buyers in real life adapt to how successful they are. I mean, they do experiments. I did something to see. In that way, I learn about the seller's strategy, but I also learn about customers, if I win, how important different X's are. They might adjust their bid. I recognize it.
Yeah, very good question. So there might be the case that the buyers also don't know their valuation themselves, And in fact, I have a work that look at the learning problem from the buyer's perspective, what would happen if they don't know their valuation ahead of time. But just in this work, we just try to focus on the seller's problem. Yeah. Yeah. Yes?
In the previous slide, the PIT is just the price you're going to pay always, even if you lose the auction, or is it 0 if you don't get the auction?
So this is the actual, the payment that the buyer pays. So it is going to be 0 if the buyer loses, and it's going to be the maximum of the second highest bid and the his own reserve price if he wins. Thank you for your question. Okay. So let me, now I think it would be a good time to summarize the main contribution. We consider two different settings. One is the setting when the market noise distribution is known, and for that we propose a policy called CORP. And then the regret bound of this policy is in the order of D, log dt, log t. So just to make it simple, it's in the order of log t squared, if I want to make it simple. And then where t is the total number of items that we are going to sell, is the length of the time horizon, and d is the dimension of the contextual information. And when the market noise distribution is unknown, we have another policy called the SCORP that get the regret bound in the order of t to the power of 2/3. So what techniques do we use for that? So these are actually the main two techniques that is going to help us to get a low regret in that setting. So instead of using the actual bid to set the reserve prices, we are going to use the sensor bid. Yes?
So the regret is not scaled with the number of advertisers there?
Yes, it's linear in the number of advertisers.
So it is scaled with that?
Yes, that's true. Yes. But then usually when they represent these things, so that would consider as a constant, so you don't put it in the regret one. Usually. So N, it depends on the inventory, it depends on the web publisher that you are actually running an auction for. So because this is being recorded, I cannot tell you the exact number, but then it's not don't think that it's like a 1 million or something. So if I...
Per advertiser. Maybe you can divide by N. So this is total regret.
This is total regret. Yeah, if you divide it by N, that actually... Yeah, you can also... Yeah. If you compute a normalized regret, the N will disappear. Okay, so the techniques that we are going to use to get a low regret is that instead of using the actual submitted bids, we are going to use sensor bids. This is very important. I'm going to elaborate on that later. And the other thing that we use to get low regret and incentivize the buyer to act truthfully is this episodic structure of the policies. So these are the two techniques. I'm going to give you a very detailed information about these two techniques, but that's going to be the high-level techniques that we use. So now let me also overview some of the related work. There is a good kind of a large literature on non-contextual dynamic pricing with learning. But then one thing that is actually differentiate our work from this work is that our work is contextual. And when it is contextual, it's much harder because you are not looking for optimal fixed prices. You are looking for the best mapping from the context to prices, which is actually much harder. And also, this line of literature does not consider a strategic behavior. Also, there is some recent work on contextual pricing when we don't have strategic buyers. This is also, as it's obvious, so one thing that differentiates us is the fact that the buyers in our setting are strategy. So let me also show you a couple of papers that are more relevant to this work. And I'm going to, these works, all of them consider a strategic behavior of the buyers. And there are a couple of dimensions that are important. So first of all, whether or not they can consider contextual setting, whether or not they can have multiple buyers, or how rich their valuation model is. Can they have a noise in their valuation model or not? So these two papers, it's not contextual. It's only for a single buyer, but they have noise in their valuation. Then Amin et al. Paper, it's contextual, but then it's only for a single buyer case, and there is no noise. There's also a paper by Hamid and Yash. It is not contextual, but they can have multiple buyers. But one thing which is important here is that all the buyers needs to be the same. So it's a homogeneous setting. And they can have noise. So our work is the first work that actually is contextual. It can consider strategic buyers. We have multiple buyers, and we have noise in valuation.
So these assumptions are appropriate for proving the thing, having the results on the end. But practically speaking, so the models do not really exist. You have data. So are the algorithms different?
The algorithm is very different. So actually, the fact, so for example, let me talk about the Hamid and Yash paper. So in Hamid, the third one. So they assume that the buyers are homogeneous, which is actually a very big assumption. And they exploit that assumption to design their algorithm. So this is, yeah. So
the choice of match, which is in the end
Yeah.
what the output is of this, should depend on the sequence of X's that you have seen, the sequence of data, no? Which I suspect for Canoia, the second paper is not, they don't have X's.
They don't have access.
So your method, the algorithm, not the proof,
Yeah.
utilizes the history of the X's, I would imagine. Or not?
Not, but then it's contextual. We take advantage of the fact that the prices are, we take advantage of a heterogeneity among buyers. We can capture that in the policy that we offer. And that's actually a hard thing to do, because if you look at the pricing policy offered by Kanouria and Nazarzadeh, they are going to use the bids of other buyers to set the reserve price of the other one particular buyer. And if the buyers are heterogeneous, this approach is not going to work. I'm actually going to elaborate on this further later. Okay. So just to put things in the context and just one-line summary for this slide. So the fact that we consider all these bids, our work is contextual, it accommodates multiple buyers, is not only like make the problem technically difficult, it's also the model is much closer to what's happening in reality. Because in reality, buyers are heterogeneous. In reality, we have contextual information. And now we have a pricing policy that can incorporate all of this at the same time. Okay. So now let me talk about our core policy and remind you of the settings. So in that, here, the market noise distribution is known ahead of time. And what is the benchmark? The benchmark is the clairvoyant solution that knows the preference vector of the buyers ahead of time. And based on our proposition, if the seller or clairvoyant knows the preference vector of the buyers, the optimal prices for buyer I, given context S, is going to solve this optimization problem. So note that this price that I have here depends on, it has index I, so it's different for different buyers. And also for different contexts, the price is also changing. So it's personalized and contextual. So this is like a very strong benchmark. And then also the benchmark is measured against truthful buyers, because if the preference vectors are known, there's nothing for the seller to learn, and there is no point for the buyers to manipulate the seller, because the seller knows anything and they are going to be truthful. And one other thing that I would like to mention is that according to this proposition, when you are optimizing reserve prices, the problem is going to be decoupled across buyers. That means that the optimal reserve price for buyer I is not going to depend on the contextual, it's not going to depend on the preference vector of the other buyers. And just, excuse me. Okay. So it's not going to depend on the preference vector of the other buyers and number of other buyers. And just to give you where this optimization coming from, this is argmax of y times the probability that the valuation of buyer at time t is greater than y. And if you replace the formula for the valuation, you get some expression like that. Okay. Now, what is our goal? As I said, is it me or? Sorry about that.
Doesn't like the proposition.
Yeah. Okay, so hopefully it's going to solve the problem. Okay. So then we wanted to design a policy that gets low regret. And what is seller's regret? Remember that the seller does not know the preference vector. And here's the definition of the regret. So the regret is the worst case cumulative regret. And the worst case cumulative regret of a policy pi is defined as the difference between the revenue of the optimal policy and the policy and revenue of the policy pi. And the worst case is with respect to this any preference vector and with respect to the feature distribution. So as long as we don't, we are computing the worst case with respect to that. Getting low regret with respect to this benchmark and according to this definition is going to be challenging because the benchmark is against truthful buyers. And also, as we discussed it in the previous slide, in the benchmark, we are having personalized and contextual-based prices. So that as a result, we need to find the best mapping between the context and the buyer ID to the reserve prices. Okay. So here is our core policy. I'm going to first talk about the main feature of the core policy using this slide, and then I'm going to show you more details in the next few slides. So one of the interesting features of the core policy is its episodic structure. So the core policy starts with the episode of length 1, and then the length of the episode gets double, and it just... It's okay. No, I need to solve this, so sorry about that. Yeah. Good.
I just muted the whole so your computer.
Okay, thank you very much. And sorry about that. Okay, so the CORP has very nice episodic structure that is going to actually help us to get a low regret. So at the beginning of each episode, we are going to estimate the preference vector. And when we are doing the estimation, we are only going to use the fresh data. We are getting rid of the old data, and I'm using that only the data that from the last episode. And then when we are doing the estimation, we are only going to use the outcome of the auction. These are the two important features of the core policy that is going to help us to get low regret. And then you will see these dark bars in that line. So these dark bars are random periods in which we have this exploration. In any period in episode K, we are going to do exploration with probability 1 over length of the episode. And when we are doing exploration, we choose one of the buyers uniformly at random, and we set the price of this buyer uniformly from 0 to B, where the B is the upper bound on the valuation. And for the rest of the buyers, we are going to set the reserve prices to infinity. Then in the rest of the periods in each episode, we are going to have exploitation. In exploitation, we use our estimate of the preference vector to set the reserve prices. I'm going to talk about exploitation in more details in the next few slides. Okay. So this is actually one of the most important slides of today's talk. So I'm going to explain why episodic structure is important. The episodic structure is important because of two reasons. So first of all, I want to remind you that buyers discount the future. So they are less patient than the buyers, so they care about getting a utility right now instead of getting a utility in the future. And on top of that, buyers are utility maximizer. And if they want to lose something, they hope to gain something in the future. Okay. So consider these two things. And now let's go back to the core policy. And assume that there is a buyer who submitted an untruthful bid, like in some period in episode K. So for this buyer to see the impact of his untruthful bid, he actually needs to wait until the beginning of the next episode, because that's the place that this bid is going to be used in the estimation of the preference vector, and it's going to have some impact in setting the reserve prices. So as a result, there is always some delay between the time that the particular buyer submits an untruthful bid and the time that this buyer is going to see its impact. And because buyers discount the utility, and they want to get the utility right now rather than in the future, so then the buyers are going to be less incentivized to bid untruthfully. So that's one thing. The other thing is that imagine that one buyer again submits an untruthful bid here. This untruthful bid is only going to be used once in the estimation of the preference vector. Because every time I'm updating the estimation of the beta, I'm getting rid of the old data. And as a result, this episodic structure is going to help me limit the long-term effect of untruthful bids, and it's going to incentivize the buyers to actually to be truthful and not to lower their bids. Any question? Yes.
Could you contextualize what an episode is in reality? I'm not sure I understand.
So episodes, think about like you are running an auction for a new website. So at the beginning, a new set of buyers. So at the beginning, you don't have a lot of data, and then so because of that, you would like to do more exploration. But as you are getting more data, so you are become more confident and more confident. You're going to update your beta less frequently. So this episode is actually think about it as a time period.
Okay. But I guess, so how are you determining the length of the episode?
So you can, so the length of the episode at the beginning starts from 1, it gets double, etc. So you can run this algorithm in a daily manner. So then in that case, the T is going to be billions of auctions, or going to be in the order of billion, or you can run this this policy in for a weekly in a weekly manner. So it depends how you want to use it. So now let's understand how we are going to do the exploitation, and we have two main questions. So first of all, how we are going to estimate the preference vector, and the second thing is that how we are going to set the reserve prices. So the first question. Okay, so we are going to do the estimation, and if you remember, our goal is to make sure that the buyers are not going to act strategically and they are not going to be untruthful. So if we have this goal, we may say, okay, just relax, just chill. I'm not going to use your bids. If I'm going to set your price for you, I'm not going to use your bid. But then, by doing that, I'm hoping that the buyers are going to stay truthful and they be relaxed because I'm not going to use their bids directly in setting their prices. But unfortunately, this is not possible. Like going back to the Dimitri's question and Yash and Hamid's paper, this is not possible because if I want to use the other bids to set the reserve price of one particular buyer, these buyers needs to be like similar, but there is a high level of heterogeneity in the market. So I cannot just tell them, I'm not going to use your bids. I have to because every buyer has its own characteristic. So let's relax this assumption. Say that definitely we cannot tell you that I'm not going to use your bids, but I'm going to tell you I'm not going to rely too much on your bid when I'm setting your prices. Okay, that seems better and more doable. And if I want to implement that, there are two approaches that one can think of. So one approach is using noisy bids and have randomized algorithms. And this approach has been used by Mahdian et al. And Makshari et al. But then one of the drawbacks of this work, this thing is that for this approach to work, you want to assume that the market is really large, meaning that each single buyer is not going to have a significant impact on the revenue of the seller. But that may not be the case in practice. You may have really big buyers in the market. So then we decided to actually take a different route and use sensor bids in our estimation. And here is how we are going to do it. So when I'm estimating the preference vectors, I'm not going to use the bids of that buyer directly. Instead, I'm only going to use the bids submitted by other buyers and the outcome of the auction. What is the outcome of the auction? This binary signal, which is 1 if the buyer wins, and is 0 if he does not. So, and when I'm saying by sensor bids, I mean like this outcome of the auction, because this is not the bid directly, but it's actually, this outcome depends on the bid, but in a indirect way. Okay. So then, based on that, we are going to minimize the negative likelihood function of the outcome of the auction, assuming that the buyer I is being truthful, which is going to be this expression. Just don't panic because it's simple. So this is QIT is 1 if the buyer I gets the item times the log of the probability that the buyer wins. And this is 1 minus QIT is 1 if the buyer does not win times the log of the probability that the buyer does not win. And as I promised, I'm only using QIT, the outcome of the auction, and the maximum bid submitted by others, B minus IT plus. Okay, so why this is a good approach? Because think about the buyer. If as a buyer, I want to change the estimation of the preference vector, this buyer needs to change the outcome of the auction. It needs to change the QIT from 1 to 0. Which actually implies that if the buyer was truthful, he could win the auction. Now, if he wants to change the preference vector, he needs to reduce his bid to the point that he becomes the loser. And then because of this change is going to be really costly for the buyer. And as a result, buyer is going to have less incentive to do that. Okay? And that's the main idea behind using the sensor beads in setting the preference vectors. Now the second question, how we are going to set the reserve prices. So to set the reserve prices, we are going to get inspired by our benchmark. Remember that our benchmark solved such optimization problem. But the benchmark knew the preference vector, but we don't. So just instead of solving this optimization, we are solving something similar. And instead of preference vector, we are going to replace it with our estimate of the preference vector. Okay. And here's our theorem, what regret bound we are going to get. So the regret bound of the core policy with respect to the benchmark that knows the preference vector is going to be in the order of d log td times log t, or for sure log t squared. Just I'm going to give you a one slide proof to give you some idea how things work. So because the buyer is untruthful, there are like 3 important factors in the regret bound. Delta 1, delta 2, delta t. So I'm going to talk about each of them. So delta 1 is coming from the estimation error. Even if the buyers are truthful, the seller needs to gather data to estimate the preference vector. And there is always some error because some regret because of not knowing the preference vector. And you can show that the regret bound is going to be proportional to the error in the reserve prices, which is related to the error in the preference vector when you are doing the estimation. And if you use the property of the maximum likelihood estimation, you get something as like log t squared. Then delta 2 is the regret that you are suffering because there is a mismatch between second highest valuation and second highest bid. Because if the buyers lower their bids, that means that the second highest bid actually goes down, and the revenue also depends on the second highest bid. And we show that this delta 2 is also in the order of log t. And the last term is because of the change of the winner. If the buyers act truthfully, the winner is going to change. And then when the winner is changing, the reserve of the winner may actually go down. So we bound this delta 3, and we again show that it's in the order of log t. Okay. So then the second part of the talk is about SCORP, but I actually knew that I probably am not going to have time for that. So do you want me to go over it like very briefly, or just jump to the conclusion? Okay. Okay. Just I'm going to show you the regret bound of the SCORP. We get, when the distribution f is unknown, we get t to the power of 2/3. And here is the conclusion. So motivated by a display advertising market in which both sides of the market had access to detailed information about the item being sold, we designed a dynamic pricing policy that offered personalized and contextual-based prices. And in such a setting, one of the main challenges is the repeated interaction between the buy side and sell side. And the buyers may want to manipulate the learning algorithm. So we designed 2 policies that are robust to such behavior. And the main techniques that we use to make it robust is first the episodic structure of the policy, and also using the sensor bids instead of the actual bids in doing the estimation and setting the prices. And we had these 2 policies. CORP is for the known market noise distribution. It gets the regret bound of log t squared. And then we also have a SCORP that gets the regret bound of t to the power of 2/3. And I'm going to finish with this slide. So I only talk about display advertising market as the main motivation behind this work. But this work and the main insight can be also used in other business-to-business online markets. So in the business-to-business online markets, the buy side and the sell side, again, repeatedly interact with each other. And at the time of purchase, they have access to detailed information about the item being sold. So think about, for example, cloud computing and AWS, or Staples when they sell products to big companies. So we believe that our work can be also applied to such a setting. So with that, I'm going to wrap up my talk. And thank you guys for listening to my talk. And thank you for having me.
Securities market.
Security markets?
Yeah.
Yeah, I think that would be also because I can imagine in the security markets, both sides of the markets interact with each other repeatedly and they have access to, yeah, that would be like a good extension for that. Yeah, definitely. Thank you. Yes.
Are you assuming that the buyers use the optimal non-truthful strategy, or is it such that your mechanism makes buyers truthful?
So it's the mechanism is not going to make them truthful. They're still going to be untruthful, but then we show that the amount of time that they're going to be untruthful is going to be in the order of log t. So we limit the number of times that they are going to be untruthful. Very good question. Oh, Nate.
But when you were bounding the CORP, whatever it's
CORP.
called? CORP, sorry.
Yes.
The delta one term, so you
Yeah.
were summing up the norms of data?
Okay, never mind. I just got it. Because the norms do reduce at 1 over square root t. So that would
No,
sum.
it was norm squared
Okay.
because we use the Taylor expansion in the regret bound, so then the regret become proportional to the mean square error in reserve prices, and then because of that, it's become proportional to the norm of the preference vector squared. So
Okay.
and then yeah,
And then so you get the log t,
it's
not the
log
square
t.
root t.
Yeah,
Okay.
exactly. Very good point. Yes.
Sorry.
Because you mind using it's about the episodic structure. You talk about the interval.
Yes.
Yeah, because you're using the latest data. I guess it's the temporal data
Yeah.
on that reserve price. So how do you classify the interval time? Because it's a time series rule based on the time, running hours. So how do you set the interval? Yeah.
So it has this exponential growth, the episode. So it starts with the length 1, become 2, 4. It's going to be 2 to the power of, episode k has a length of 2 to the power of k.
Do you necessarily like come up with the average or mean of the condition of the bid and reserve price and do a mean and then do a distance, like k nearest neighbor between them, then you set an interval? Like
You mean to find the length
Yeah,
of the episode?
yeah.
No, this is the way that it's constructed is prefixed, but then maybe we can one can maybe design an algorithm that has this adaptive length, but then we show that even if you go with the fixed length, that would do the job. Yeah.
Okay.
Thank you for your question.